Thank you, Ted. Nice to see you all. My name is Monica, as Ted said. I'm a senior lecturer at Cranfield University. My area of research overlaps between statistics, state-of-the-art technology, drones mainly, and modeling of environmental processes. And today I'm just going to cover a little bit about the use of drones and artificial intelligence for flood extent mapping and flood damage assessment. So hopefully you can all see the screen now.
Yep, that looks great.
Great. Okay, so I will start just with key principles of what the situation is in UK, leading into other countries. Approximately we have 5 million properties in England that are at risk of flooding. And as we have seen in previous presentations, the annual flood damage is estimated to be approximately 1 billion. With the price of each house in terms of repair ranging between 10,000 and 50,000 pounds. So it's a substantial amount of funding that is required to maintain flooded houses back into shape. And what we usually encounter is that either for emergency response, local authorities, or loss adjustment insurances, we really need to gather data during or after the flood event as soon as possible to make prioritized decisions to ensure that the resources are allocated in the right places and that areas that have been badly affected are targeted adequately. So the usual range of time that we require this information within is 48 hours, 24 to 48 hours. We require high resolution, generally at property level, so that even if we can identify whether there are resistant and resilient measures, we are better off. We usually require quite a large area to be covered. Depending upon the flood event and extent, we can have several hectares of damage. And in some cases, we require the data fast enough to be able to validate flood models that are running during the flood event. So with this in mind, we have multiple methodologies that are available out there to collect data. Perhaps the most relevant ones are satellite imagery, image from aircraft, and LiDAR data. And you can see in that table over there that the data can be collected pre-event, during the event, or post-event. And depending upon the type of methodology that we are going to use and the purpose for which the data is being collected for, some methodologies are more suitable than others. When we focus during the event and after the event, usually we experiment some difficulties with satellite and aircraft imagery. So usually during the event and after the event, what happens is that we have cloud cover, low cloud cover, and the satellite imagery cannot give us any information because everything is covered by the cloud. And the same happens with the aircraft. It's not possible for us to gather any data. Sometimes we have a lag between the satellite data and the flood event. So even when we collect the data that is useful, it's not possible to see anything flooded because it's too late by then. And for those data that can't penetrate the cloud cover, we find other difficulties. So sometimes the angle is too oblique and we cannot see where the water is, or we cannot identify the difference between the water signature and the urban signature, so the concrete. So for example, on the image that you have here on the right hand side, you have two rivers, the Severn and the Avon, and all the area that is within the red square has been flooded. But just because of the satellite imagery not being clear enough, it's very difficult for us to see whether there is water and whether there is concrete. It's quite difficult to identify. We also have other limitations with current methodologies, which rely on the fact that in gusty conditions it's very difficult to fly with aircraft. Sometimes the quality of the products obtained is not good enough. The resolution is not fine enough for us to make informed decisions. And when we have to collect data when we go in the field, either it's too late or it's too cost consuming. So we thought that perhaps drone technology, especially combined with artificial intelligence, could provide a step forward into addressing some of the challenges and giving us an improvement on the current information that we gather during and post-event, and also pre-event as well. So the key 5 things that I would say that drones could help us with when we thought about this were that they could give us increased accuracy. So some of the imagery that we collect from drones is around 2 centimeters of resolution, so it's quite high. You can see pretty much everything in a house. It allows us to deploy the drones when and wherever, as and when needed, so it's fast deployment. And usually the products can be obtained in less than 48 hours. It is cost efficient. Once you have bought the equipment, the cost of flying is just going to the site and being able to deploy the drone, assuming that you don't crash it when flying. It happens. You also can target urban areas if you have the right permissions, which is difficult with SAR data. And also it enables us to produce some novel visualization techniques for the flood event, for the extent and the impact, based on this combination of drone processing data processing, as well as artificial intelligence. So moving on with this idea, what we did is a test divided in 4 steps to see whether this could really work and see if what we thought initially that was a good idea could really be implemented. So in the first step, we wanted to test the technology. Then we wanted to see whether we could develop these algorithms and they could actually help us using artificial intelligence. Then we thought about how can we visualize this? And finally, how can we develop a robust framework? And the work that you will see from now on in these slides is work that is still undergoing. So we have not finalized. These are just preliminary results. So back in 2015, a few years ago, we thought that we should test the technology, the drone technology, and we selected a case study area, a local case study area, Cockermouth in Cumbria, north of England, and we selected a storm event that was quite relevant, Storm Desmond, which had estimated annual probability exceedance of 0.0101%, which is really low. It was an unprecedented event with really windy conditions, 81 miles per hour, so that's 130 kilometers per hour, really extremely windy, and caused severe disruptions to the area. So approximately 5,200 homes were flooded across Lancashire and Cumbria, and many of them lost electricity power, so they didn't have any supply. So in terms of emergency response, it was quite a big incident. The image that you have on the left-hand side shows Cockermouth, the town market. You can see that there are 2 rivers, the Derwent and the Cocker. We will see that in the next slide. And this digital elevation model, the terrain surface that you can see in there, is just showing us the areas that are more prone to flooding. So anything that is in blue color is highly likely to get flooded. Anything that is red is less likely to be flooded. And you can see that the town market is just sitting in the confluence of these 2 rivers, which makes it quite dangerous in terms of flooding. Is usually a big event that occurs quite frequently. So just to show you again the area, as I said, we have these 2 rivers just going through the area that meet at the center of the market town, and then floods events usually occurred in all the urban area that you can see there. We tested the methodology, see if we could collect some data few days after the event, because it was very difficult to fly 3-4 days after the event. The winds were still really high. And we deployed a drone that was a Sirius Pro, which is the one that you have in the image, which is reasonably easy to operate. It can go very well in gusty conditions, so it's able to fly when the wind is approximately 65 kilometers an hour. And it's quite light to deploy it. It has an battery endurance of 50 minutes, which means that when it flies, it can gather a substantial amount of data. So having said that, and going back to Cockermouth, again, you can see the Derwent over here and the Cocker. The areas that are colored are the data that we managed to cover during the event. We did 2 flights within 4 hours. That was including the location of the ground control points. We managed to cover around 140 hectares approximately. These are the flight plans. So this is how the drones were flying, or the drone was flying on the day, and how the area was covered in each multipass that we did. So in the first step of testing the methodology for drone data collection, we succeeded and we proved that we are able to collect the data. But then we had to assess whether the data was good enough or not, and whether we could develop these artificial intelligence algorithms. And we are still working on that. So the work that you will see is preliminary. We have currently a funded project through Innovate UK looking into that. So the image that you have in here, and apologies for not showing you the nice color image in high resolution. It's mainly so that people cannot recognize the house, and because the detail of the image is very high, so that you cannot recognize the house, but you can have a clear picture of what we can see. In the first initial stages of data processing, we produce this type of images. This is a house, as you can see there. And as the flight took place a few days after the flood event, people already had the time to pile things outside the house. So you can see some piles of rubble and debris from within the house, sofas, fridges, things that had been damaged, piled outside, as well as in the garden. So that could work for us as an indicator of houses being damaged, and how we could calculate the intensity of the damage as well as the extent. So with this in mind, we did a sequential process for the development of the algorithms. First of all, we did it visually. We collected the data, as we have seen, and then we identified any proxy variables that could indicate that flood had damaged a house. And these were beanbags, natural debris, exposed mains, scours, skips, damaged goods like cars, water that was still in place, access to bridges compromised, as well as dehumidifiers that already were in place to clean some of the houses. So that was the emergency responders already cleaning the area. And what we assumed was that any houses that were close to points where these proxy variables had been identified were quite likely to be damaged, and we assumed that those houses were damaged. So for example, in here you can see in orange houses that we assumed that were damaged because they were close to 3 points that indicated that there were beanbags and skips close to those houses. That allowed us to make some estimations about which properties had to be prioritized in terms of emergency response, also in terms of schemes from government perhaps to provide resilient and resistant measures, but also in terms of loss adjustment, where the insurance had to go and check which houses had been damaged and by how much. So pretty much this is the scene that you can see when you're walking around the area. So that will be what you will encounter, and this is what you can see from the air. What we try to do next is see if the artificial algorithms, the artificial intelligence and machine learning algorithms could help us to solve this problem a little bit faster than doing it visually. And in these initial preliminary results that we have on the right-hand side, what you can see are the houses. Again, the imagery has been degraded so that you cannot recognize which house is which. These piles of rubble and things that people have piled out because the houses were damaged, you can see them on the right-hand side. With the algorithms that we have already developed to date, we can start seeing that we can recognize automatically the houses, so you can see them in red, all the other features that are in the gardens, including water as well. But also, most importantly, in yellow, you can see that the software is already, the algorithms are already recognizing the piles of rubble that people were identifying. So for example, in here, that corresponds to this house, and it's matching quite nicely. You can see in here as well that it's matching with what we have in this house. And I can assure you that there is rubble here as well and here. So something that was taking us 7 days to process manually, it became a 15-minute job with this tool that you can see over here. We are still working on improving the different categories that we can identify with the artificial algorithms and see exactly how we need to develop the algorithms next to make sure that we recognize more detail from these images. But it's work that is still undergoing. Still, we have 1 year to go. So we tested two that work nicely. Then we developed, we checked what were the visualization tools that we could identify. And we have multiple. I'm going to show you two because we are time constrained. One of them is the usual map. In here, what you have is in gray in the background is the area that we surveyed at the time. So all that was the data that we collected. And each of the squares that you have in here are squares indicating level of damage. We had to aggregate the information just to make sure that we didn't identify single houses and people could not pinpoint a house. But if the information is required at house level, we can provide that as well. So the red line that you can see in there is the fluvial flood extent. So one would expect to have all the houses within that fluvial flood extent flooded because it's water that is coming from the river. But you can see that other areas outside the fluvial flood extent, that was a little bit of a surprise to everybody, were also flooded. So you can see all the damage there. That meant that this town market, which we expected to be mainly affected by fluvial flooding, now was affected by both fluvial and pluvial, with the pluvial flooding generating substantial damage. We have calculated the amount of damage. It's in a publication, so I will refer you to go there and have a look if you want to see exactly what the amount of damage is in economic terms. In general, if you look at the color of the squares, what we have is orange to blue. Blue indicates large flood damage, and it ranges between 250,000 and 500,000 per square. So you can see that those areas here are highly damaged. With the orange, the lower category of damage being around 1,000 to 30,000 pounds. We explore other visualization techniques, obviously generation of maps that cover the whole area with this artificial intelligence map, giving us more detail. But also in line with establishment of standardization of protocols for risk acceptance and communication, we thought that it would be quite nice to be able to produce a tool that people can relate to. So we have been working on the creation of 3D models, as you can see, hopefully you can see in this video. This video is just showing the area on the day that we collected the data. It's not video as in recorded video, is video processed from the drone products. So this is generated from the images, okay? And it's generated with a software, a computer program. It's realistic because what it does is taking the information from the pixels that we have in the image and putting some elevation to it and generating the features. And it's allowing us to see, for example, where a scour is occurring. Yeah, so we can see in the areas where erosion happened. We can also see which bridges were compromised. So the breeze perhaps were just blocking the bridge. Hopefully we are going to see another example here soon. Okay, here as well. So you can see that there are debris over there that are compromising the bridge and therefore the structure is being put in peril. We can also see houses that have been badly affected, and hopefully we will see a little bit more of detail in a second. Where erosion is happening close to the houses, pipes are being exposed, and debris in general are being, look at here, you can see the debris on the bridge. You can see the erosion next to this house, which is pretty bad. That was a really badly affected area with the mains being exposed as well. And also piles of debris all over the place from people that were just trying to clean the area and clean their houses. So we thought that that could be a good idea to, again, communicate risk and increase the perception of the damage that flood is causing. There are other tools, but as I say, we don't have the time today. So at the end, we thought that we should bring all this together in a framework that will help us on the deployment of drones somehow and the implementation of artificial intelligence. You can read more about this framework in the publication that you have here at the bottom, But in brief explanation, what we have is a big framework, complex framework on the right-hand side. I know that you cannot read it, it's just for you to illustrate the complexity of the analysis, where we have divided the framework in two axes. At the X one, you have the emergency response, whether the data needs to be collected pre-event, during the event, or post-event. And then on the Y-axis, what you have is the catchment flood response. So here is how fast the catchment responds to the flood event. And depending upon the combination of when you want to fly, the pre, during, post-event, and the catchment response, we are able to say when drones are more suitable or not for specific tasks. So for example, for pre-response, what we really need to look at is at data that can gather information for improved flood modeling. During the response, the drones are being used for emergencies. So for example, for communication of events happening, sound events, people being warned about the flood happening. And then post-event, what we really want is to fly as fast as possible so that we can see exactly where the wrap marks are, where the flood extent is, and collect all the data that we cannot collect by working within the area. The key principles of that framework are summarized here. And this is because we are working at international level with multiple countries, specifically India, to make sure that we can transfer lessons between two countries. And that makes the need for the framework to be transferable to multiple countries. So on the right-hand side, what you can see is Cockermouth, is an image from Google Earth. And you can see that it's very nice layout of houses, very well distributed. The distance between houses is lovely. And within the context of emergency response, it's easy to act. You have a planned route. You have plan B if the route is compromised. But in that setting, it's easy to identify when and where you need to fly the drones. But if we move to the case of India, we want to make this framework transferable to that setting. The situation is completely different. What we have are developed areas with slum areas where the intrinsic configuration is very complex. There's no map available about it. And during the event, you don't know exactly which entry and egress areas, routes are going to be compromised. So it's a completely different setting, and the framework needs to include that flexibility. It also needs to make sure that you have comparable results, no matter in which areas you are flying, so that you can standardize outputs and really take prioritized decisions. You need to make it compatible with country-specific emergency response, so we make sure that the framework was working in that way. As I said, it should enable prioritization by being you objective information. And also it should standardize risk perception and communication. So my concluding remarks are that, well, the use of drones and artificial intelligence is in initial stages, but it can help to identify the damage of multiple sources of flooding in more detail than we currently do. It can facilitate better and faster estimation of the extent and impact of a flooding event. The full extent of the technology and the potential of the technology has not been explored yet, and therefore further studies are required. So I encourage people to get on and try their drones and see what they can gather. Obviously, always in a legal framework, okay? Don't break the CAA regulation in UK. Integrate the technology with flood management preparedness and response, and ensure that we can progress that bit of science further. And then we know now that the use of drones can really contribute to identify the properties that are at higher risk of being flooded and have been highly impacted by the flood events. So with that, I will just conclude my presentation and open the floor for questions.